Okay, let me start by recapitulating the concept of the transformation that we called homothety in my last lecture. So homothety, remember the homothety with center P, so this is a point, and a number that's called ratio of similitude, was a map from the Euclidean plane into the Euclidean plane. Well, I'm identifying the Euclidean plane with R2 as usual, which does the following thing. X, any point X, I'm writing the vector notation, is mapped into P plus alpha times X minus P. Well, geometric portent of all this thing is, of course, that there is a center P, and well, the point P is mapped into itself, obviously. And if you have another point X, if you have a point which does not coincide with P, then to find this image, all you have to do is to take the vector Px and multiply it with alpha, okay, so as to obtain the image X prime. So this is the image of the point. To briefly give you some concrete examples. For instance, if you take the situation, okay, alpha, let's say something like, if you take alpha equals 2, well, it looks like, obviously, okay, so that's your point P. The vector Px is multiplied with 2. So let's pick up another point. To obtain a mental picture of what's going on, if you take another point y like this, okay, and that will be mapped into y prime. Now, it's ironic that I remember my opening remarks in my first lecture saying that this whole set of lectures, this whole course of lectures, will possibly be a gigantic tribute to the theorem of Thales about the parallel lines and the way in which the parallel lines separate proportional pieces from transversal lines. Now here we are again. Okay, check that the lines, okay, so x is mapped into x prime, y is mapped into y prime. You can readily check that just because of the theorem of Thales, the line xy is mapped into the line xy and line x prime, y prime are in fact parallel. So let me make a remark. A homothety maps a line into another line, and let me remark that this is a parallel line in fact. Okay, so that hardly requires any further elaboration. Yet, as I said, I want to fix the pictures in your mind. So, for instance, let me notice that if you take alpha equals 1, for instance, that's a trivial situation. Alpha, if you've got alpha equals 1, Well, any homothetic with any center and ratio of similitude 1 is just the identity map, so this is just a very trivial situation. You hardly need to talk about that. So let me just point this out. Now, perhaps it might be a good idea right at this moment to look at what happens, for instance, if you take alpha equals minus minus to x will be multiplied by minus 2, which means that this is what you're doing. You're producing the line px till you reach a point x prime, so that p in fact divides the line segment xx prime in the ratio -1 to 2. Okay, so that's the kind of picture that you get. And perhaps, okay, perhaps there is one thing that we should mention. Again, it is the case where the ratio of similitude is -1. Now that is something rather remarkable. But alpha equals -1. If alpha equals -1, then of course what you've got is a situation like this. So that's the central homothetic, central similitude, central homothetic. And a point x is of course mapped into a point x prime. Okay, so that the point P, the center, is actually the exact center of the line segment xx prime. Okay, so now that means that what you have conceived as the homothetic with center P and ratio of similitude -1 is exactly the half term about the point P. Okay, so that's yet another coincidence that you should perhaps be thinking about. Right. Okay, so I think I briefly recapitulated what was done in my last lecture, and so you have recalled the definition. Not only that, you have got a good picture of what's happening under homothetic. So in fact, so a homothetic is a transformation which fixes a point and expands or contracts the whole repeating plane in the same ratio all over homogeneously. So it's either an expansion, it's either a dilatation or a contraction. So that's the big picture. And this is the kind of thing which of course preserves lines, and in fact lines go to lines, in fact parallel lines. So you've got this. Okay, so the natural question to ask, what happens? So that's my today's lecture. What happens to a circle under a homothetic? Okay, so the effect of a homothetic on a circle, on circles. The effect of homotheties on circles. Well, this can be answered very easily and very fast. So let me just directly go to the question. Okay, so I have not used that notation, but let me devise a notation for circles because we shall need this kind of notation for brevity. Let me denote the circle with center O and radius R, big R, as big gamma OR. Okay, so that's simply the circle of center O and radius R. Okay, so this kind of notation will be useful. Okay, so what happens to a circle with center O and radius R? Okay, so let me first draw my circle. Okay, here's my circle with center O and radius R. Okay? And I will take a point P somewhere. And I would like to know the effect of a homothety with homothety center with center of similitude P and ratio of similitude alpha. Check that alpha can be any number. I have only excluded the possibility of zero. That would be wrong. Silly. Okay, so here we are. Here is my circle. And let us see what happens to this circle under a homothety with center at P. Good. So, for purpose of illustration, let us imagine that alpha is something like 1.5, 3/2. Okay, so just for purpose of illustration. So if you take any point, okay, so first let me ask the following question: what happens to the point, the center A? Well, the center O is simply sent into a point O prime, perhaps somewhere here. Okay, O prime. And let O prime be, in fact, the image of O under a homothety with center P and center of similitude alpha. Good. Now, the next thing that you have to do is to see what happens to a point actually on the circle. So let's say, for instance, I take a point here, X. Now this point is mapped under a homothety, okay, into some X prime. Okay, there it is. And what do I know about this X prime? I know that the ratio of PO prime to PO is alpha. I know the ratio of PX prime to PX is again alpha, so it means that this OX prime is parallel. Besides, the triangles POX and PO prime X prime are similar. So if the length OX is R, then I must conclude. So I must conclude that this length O prime X prime is of course, because I'm making a deliberate mistake. The length of OX times alpha. So this is everything is being enlarged by a factor alpha. Now the mistake is of course obvious. You see, alpha can be a negative number. Okay, so it's just so if I want to know what happens to the length, I must really take the absolute value of alpha. Okay? So that means, okay, so this is, okay, so the distance between O and X, as X moves on this circle, imagine X moves on the circle, okay, between X is off. So as X moves on this, its image X prime must move on the circle with center O prime and radius R prime R times the absolute value of alpha. Okay? So I can, if you wish, complete my picture by. Now, you see, it's always this a tragedy, you know. It's such a stupid thing to try to draw your circle, starting with the center and the radius, because you will never get it right. Okay, just as I'm not getting it right now. You always take the circle and then the center. But then in this case, I have to. So let me do my best. Okay, so there we are. But that's not too bad. I don't need to draw the whole thing. So that's the point X, and that's its image X prime And this is what's happening. That's the center O, and that's the center O prime. Okay, so there we are. So that's what's happening. So under a homothetic, a circle is mapped into a circle. That's great. Okay? Okay, so what we have is, given a homothetic, in fact we have established the following. Given a homothetic with center P and a ratio of similitude alpha, its effect on the circle with center O and radius R is quite simply is turning it into a circle O prime, R prime, where O prime, so the center of the second circle, is simply the image of the center of the first circle under the homothetic in question, and R prime is merely the radius of the first circle multiplied with the absolute value of the ratio of symmetry. That's it. So a circle turns into a circle. A circle turns into a circle. Good. Yep. Perhaps you should perhaps make a few pictures. For instance, it might help if you've got. So let's see, for instance, what happens if you have got a homothetic with negative ratio of similitude. For instance, if you've got so a very simple situation perhaps, but let us say, here is the thing, center of similitude, and let us see what happens, for instance, if you take a homothetic with center P, and let's make it very simple. -1. So so the image will have its center in O prime. So I'm just drawing the picture. Okay, and how do you find O prime? Well, you simply produce the line segment OP in the direction OP, so as to find a point O prime, so that P is the exact point of the line segment O prime. You have done it. And since this is -1, its absolute value is 1. So the image circle will have exactly the same radius, so it will be something like this. Now, perhaps this picture is not quite exciting. It's not quite exciting, but I think it would be a lot more interesting. I mean, this phenomenon of homothetic, this ratio of similitude, will become somewhat more interesting if you notice the following phenomenon: that so let's try to trace out the images of individual points. So I should make this a little larger. I'm sorry. Okay, so what's happening? So for instance, if you pick up a point here, let's say X. Okay, so where is its image? Of course, it is. Okay, it's at a point X prime, so that your P is in fact the exact midpoint of the line segment XX prime. Okay, so there we are. And it is interesting. I mean, I always advise people to look at this from a dynamic point of view. For instance, if you move X in this direction in counterclockwise fashion, this X prime will also move in counterclockwise fashion, will it not? Okay? Yet somehow, the motions will somehow oppose one another. Okay? However, in this case, X and X prime seem to be moving together. Okay? As in this case, they seem to oppose one another. And again, just do it yourself. It's very good to get a feeling for this kind of thing. Right. So a circle goes into a circle. Allow me to give you one more interesting case case. For instance, ask yourself what happens if you take a circle, and I'm depicting it as a very small circle, okay? And if you take a homothety, in which the center of homothety is exactly the center of the circle. So what happens? Well, obviously, well, this whole argument is still valid, yet the center of homothety will be fixed. So O is in fact O prime, and all that happens is that the circle is simply magnified, keeping its center, it will be simply magnified. Okay, so if this is R, then this is R prime. So you still have the same thing. So this is what happens if you look at if you use the homothety with center O and ratio smooth alpha. Of course, R prime is, as always, the radius of the original circle multiplied with the absolute value of the ratio of similitude. Okay, so that's one thing. Perhaps another interesting situation is what happens to a circle for us. I mean, these are not terribly important things, but I have found, I've often seen inexperienced people deceived by this kind of configurations. For instance, what happens? What happens if you take the center of similitude on the circle, for instance, P? Okay. Well, you see. Well, there's nothing. So let me to make the situation clear. Let me take the ratio of similitude something like 2.5. So, or let's say 3. No, 2.5. 2.5 will be basically. So this is what happens to the center, and the radius will also be multiplied by the same number. And the circle with center O and radius R is mapped into another circle which has its center at O prime and its radius is 2.5 times. So it's exactly the circle that is. Now that's difficult for me to get right. So please have patience with me. And if I obtain a terrible picture, please don't be disappointed. Okay, there we are. Okay, so what I'm trying to say is that, okay, so let me now make the situation quite clear. Okay, so here is the circle gamma LR, and it is mapped into a circle that is tangent to the original circle, like this. Okay, so if you look at the effect of a circle, or effect of a homothety with homothety center on the circle, then it is simply that the circle will turn into a circle that will be tangent to the original one, and that this picture should correspond to the situation where alpha is positive. If alpha is negative, you get a similar and perhaps even more exciting picture. Okay, so here is your small circle. Okay, and here is the point P. Okay, and let's say you take a homothety with center with a ratio similitude negative. So the center O is mapped into a center somewhere here. Okay, so I'm drawing a picture in which the center of similitude is something like -1.5. So you get something like this. So you obtain another circle that is tangent to the original circle. Okay, yet so that's interesting. So this is tangent circles. These circles are tangent. Well, internally, that's what we say. And these circles are tangent to one another externally. Okay, right. So that's very interesting. Okay, so I want you to bear in mind what happens if you have got homotheties which are in a certain way, which are somewhat spatially connected with the geometry of the circle, versus what happens with homotheties when the center of homothethy is exactly the center of the circle. Circle just grows larger. Okay, nothing happens. And if the center of homothethy is on the circle is turning to yet another circle, well, it's original to the tangent. It's tangent to the first circle, so and so forth. Right. Okay. So that's all. Circle turns into a circle under a homothethy, and you can actually construct the center of the circle, because this center is mapped into the center of the new circle under the homothethy. That's rather nice. And the radius can be found very easily by multiplying the original radius with the absolute value of the ratio of similitude. Good. Now I want to, okay, so that's the end of the question. So what happens to a circle is obvious. Now I want to ask the opposite question, the converse, which is rather important. And what I mean by the converse is the following. You give me a homothethy, you give me a circle, the effect of homothethy on the circle is the circle turns into another circle. Now I ask the other question. I give you two circles. Is it possible to construct a homothethy which maps the first circle into the other one? Okay, so given. So this following question, how much time have I left? Just a minute. Yeah. Okay. So, given circles, let's say alpha, beta. Is it possible to find a homothethy that maps alpha to beta? Okay, so I give you two circles, alpha and beta, and please keep an open mind. These two circles can be related to one another in really very complicated ways, in very different ways. Okay, so I've drawn a very simple picture for you. Check that. Let me change my notation. Let me call circles kappa and kappa prime. I'm sorry for being rather devious with my notation, but I just remembered that I've used alpha for. Okay, so that's one circle kappa. It's rather good for circles, you know, the Greek tubules being circle. Okay, so there it is. So these are the two circles. How can I find a homothethy which will send the kappa into kappa prime? Is it always possible? Well, let me give you the answer. The solution to this question is as follows. Yes, the answer is yes. The answer is yes. Yes, given two circles, it is always possible to find, in fact, not one homothethy, but two distinct homothethies which map the one circle into the second one generically. Well, generically means that up to certain very well defined and geometrically significant exceptions, Okay, so the answer to this question is that solution. I shall in a minute tell you why the solution is valid. Solution, yes, yes, yes. Is it possible? So the question was, is it possible? And the answer is yes, yes indeed. There exist exactly two homopathies mapping kappa into kappa prime. Okay, so why is that? Why is that? Okay, so generic, okay, here's the word, generically. There exists. Okay, so let me say this is generically. Generically. That means up to certain generically. So there are exceptions, but those exceptions are easy to point out, and well, there are exceptions, so they emerge rarely, and when they do emerge, well, the configuration apparently has some very simplifying features, so not terribly interesting. Okay, so how do we do it? How do we do it? Okay, so let's say the kappa be the circle of center O, radius R. And let kappa prime be the circle with center O prime and radius R prime. Now, I want a homothetic sending kappa into kappa prime. If, let me first show you the uniqueness. If, let me call it F equals the homothetic. I don't know where the center is, P. I don't know what the ratio of similitude is, alpha, if this thing maps kappa into kappa prime, you can assure. So first of all, we must have the following. We know that the ratio of the radius of the second circle will be the radius of the first circle times the absolute value of the ratio of similitude. So this is alpha. So if this is the homothetic, then the absolute value of alpha must in fact be the ratio of R prime over R. Okay? So in fact, there are two possibilities for alpha. Alpha may be either R prime over R, or alpha may be minus R prime over R. So there are two possibilities. Well, can we realize these possibilities? Let me do that. Yes, it is indeed possible. Because, okay, so let us first notice. Okay, for instance, where is P? If P is the center of homothetic, in a homothetic that sends O into O prime. Well, PO, so PO prime to PO is alpha. The ratio of PO prime to PO as directed quantities is alpha. So it means that P is in fact the point that divides the center of divides the line segment O prime in the ratio 1 over alpha. Okay, so let me do it like this. So O is given, O prime is given, and I know that alpha, so P must be the point that divides the line segment O prime and the ratio 1 to alpha. I am making a deliberate mistake, but wait for it. Don't worry, it's not a terrible mistake. It's a non-generic mistake. It concerns the exception. Now, is it so? Okay, so let us go on. There are two possibilities for alpha. Either it is r prime over r, or it is minus r prime over r. So you can do them both. So it means, here we are. Here is my first circle. Okay, here is my first circle. Okay, so that's kappa. That's the center O and the radius r. And the other is somewhere here. So let me exaggerate this equation a little bit. Okay, here is, that's my other circle, K kappa prime. So, alpha, the only possible alphas are either r prime over r or minus r prime over r. And where are they? Well, if you work with the positive one, it is a point that divides, okay, so here's this line segment. Here's this line segment. This line segment will be divided in the ratio r prime to r. So how do you construct it? Well, just take this is r prime, the radius. Just take this, okay? So actually, all you have to do is to take two parallel radii, but to make it sure, let's erect perpendiculars like this, okay? And we have got the points, let's say x prime and x. So if I join x prime, it will intersect the line joining the centers in a point P. Okay? So P, that is the one that divides the line segment O prime in the ratio r to r prime. So this is called Px. So Px, I have chosen to be exactly that point which divides O prime in the ratio r to r prime. Here we are. So let me put that frame box around it to indicate that. Right. What happens if I work with alpha, which is the negative of r prime over? Well, in that case, you do exactly the same kind of thing, however, pointing in opposite directions. Let's say, let this be y prime. So you just join x and y prime, okay, and the line intersects, of course. Okay, so let me use a little bit of color, otherwise the thing is starting to get too dull. Okay, so okay, here are the centers of the circles. I indicate them in blue. Okay, and here is the Px, the one that divides the line segment O prime in the ratio r to r prime. And here is, okay, the other one, which divides internally in the same ratio. Now we call it P int. P int is defined by a relationship model like this. P int is the point that divides the line segment O prime in the ratio minus r to Right, so internal. Now that is, well, it's finished. It's finished. So in fact, if you take homothetic with center px and I'm sorry, so let me write it like this: px and branch of similitude r prime over r, then this sends kappa into kappa prime. Well done. And if you take the homothetic with center of similitude p int, now this time with minus r prime over r as the rash of similitude, then again kappa is mapped into kappa prime. Right. Okay, so so my deliberate mistakes. So non-generic situations. Okay, I think before I do that, we must have a break. Let's have a break, 10 minutes.